Good for you. Man, I had.
All right,
Nothing.
party
That's
people.
what you ate.
Why isn't this switching over?
Not bad. You.
Okay, anybody try this over the weekend or the last couple days? I think this was the last thing I did, right? Which is a week ago, and I said, anybody try it? Too busy? It's okay, you don't have to. But there's two ways to do this, and there's kind of an easier way and a hard way. The easier way requires us to do a lot of work with matrices. And you may or not be able to do this depending on how your calculator is set up. But let's just go ahead and convert this into the Laplace domain. So 336 is just a DC source. So that becomes 336 over S. What does my inductor look like in the Laplace domain? Remember the circuit analysis? What did we do? If there's an initial condition, but there's no initial condition, so what's that? No, this is in the Laplace domain, right? Not in the time domain. It acts like a resistor as long as you put the right variables in it. Remember, the right variable is S times L, right? You just multiply the inductor value, 8.4, by S, and you get the actual Laplace resistor, we'll call it, right? Because there's no derivatives here. We're just multiplying by S. Our resistor is a resistor is a resistor. My inductor here becomes just 10S. And this is 48. Now, this is no longer I1 of, in the time domain, it's I1 of S. This is I2 of S, right? Because we're in the Laplace domain, so we can't write time domain equations. We've got to write Laplace domain. But now we can just use KVL because it's voltage drops. So we show the pluses and minuses, exactly what we do when we're doing regular old mesh analysis. And we start to write negative 336 over S plus 8.4 S plus 42. That multiplies I1. And I'm not going to put I1 of S. I'm just going to call it I1 if everybody's okay with that. Understanding that's in the Laplace domain. Minus 42 times I2. That's going to be equal to 0. So setting it up in our standard form, 336 over S equals I1 times 8.4 S plus 42 minus I2 times 42. That's our first equation, right? Our second equation is going to be negative 42 I1 plus I2 times 90 plus 10S. That's going to equal 0. So 0 is equal to negative 42 I1 plus I2 times 10S plus 90. Two equations, two unknowns. Let's go ahead and substitute. So let's solve this equation for I1. So I1 is going to be equal to I2 times 10S plus 90 divided by 42. And then we're going to stuff that into that equation. So we end up with 336 over S equals I2 10S plus 90 over 42 times 8.4 S plus 42. Whoops, sorry about that. Minus I2 times 42. Might be going a little fast in how I got there, but everybody following along what I did. It's just algebra at this point, right? All it is algebra. Nothing more, nothing less. Okay? So now I've got to go ahead and isolate my I2. So 336 over S is going to be equal to, I'll factor out I2, 10S over 42 plus 90 over 42 times 8.4S plus 42, and that whole thing has to multiply out of there. So at this point, I just have to solve for I2, right? Which means I've got a lot of math to do. So let's try and do that and see how messy it gets. So I'm going to FOIL this. So this is 84 S squared over 42. So that's the first. Outer plus 10S. Inner. Let's see, 8.4 is twice 4.2, right? So that would be 0.2 times 9, which I believe is 18S. And then lasts all of that times I2. Everybody follow along what I did there? Did I do it right? I did it kind of fast, but did I get it right? Yes. Yeah, the negative 42 is just adding or subtracting, I should say. So I can't FOIL that, but I can FOIL the 2. So let's check 10S over 42. So the 10 multiplies the 8.4, so you get 84 S squared over 42. Then I did I just did I did the first, then I did the outer. So that becomes 10S times 42 divided by 42, which is just 10S. Then I did the inner. So this is where I got a little cute. 8.4 divided by 4.2 would be 2, right? So that means 8.4 divided by 4.2 times 10 is 0.2, correct? 0.2 times 90 is 1.8. So that should be, if I did it correctly, 118S. No? I'll write it out over here. Everybody agree with that? Those are my firsts. You all okay with that? Still okay? Is that better when I show it out that way? It's still not better. What? Where did I lose people?
You're dividing 4.2 both sides.
Dividing both sides? I'm not, what do you mean?
So you're dividing 8.4 by 4.2. So you would,
Yes, I'm just dividing 8.4 divided by 4.2. And then the last one is 90 over 42 times 42 is just 90. So I'm left with 336 divided by S equals I2 times 84 over 42. Let's just call that 2S squared plus 28S plus, okay, I'm going to divide both sides by 2. So I get not 178, 168. That's an S. So I2 . I'll give you 3 minutes. Good practice for the exam. Oh, I forgot to ask, any last minute exam questions? This would be a good practice one for the exam.
This is gonna be on the exam, or like this material?
No, not this material, but partial fraction expansion will be, right? So if you can do partial fraction expansion for this one, it shouldn't be too bad. Anybody impressed with the math we got there from here? Not that hard, right? It's just doing it in, if you can, in your head. And like I said, I've got a 5th grader who's taking 6th grade math and he has to do everything on paper, and because my wife's math skills aren't as sharp as mine, I'm the one who has to quote unquote check his homework, which means I have to do it all myself. So sometimes that's like 20, 30 minutes. But I cheat, I use my calculator. I'm not going to multiply some of these big numbers out, but if there's opportunities like this where I can show him how to divide by 10 or multiply by 10, I'll actually do that with him so he can see the process, because it will make his life a lot easier.
So you divide it by 2, you get the 168 over x.
No, I divided both sides by 2, right? Because I had 2s squared plus 28s plus 48. I normally want the highest thing to multiply s by is just a 1. So I just factored out 2 from that side, and then I divided it both. I divided that on the other side. Okay. Can people in TV land hear me? Nobody has complained.
Yeah, no, we can hear you.
Okay. I was worried because I asked the question at first and nobody responded. So I was like, well,
I'm
Nope.
trying to work the problem.
no, that's okay.
It has real roots.
Ah, Arthur gave you a little hint. You found the roots. Did you do the quadratic equation or did you use your calculator?
No, I did the quadratic equation.
Nice.
To get 14 squared plus 4 times 24, which is the radical of 100, which is 10.
Yep. You got it. So since Arthur gave you the information, I'll put it up here too. Negative b plus or minus the square root of b squared. So how do you do 14 squared? I do 140 plus 4 times 14. So that should be 196 if I did that correctly. And then for a c, so 4 times 24, 96 all over 2a. Negative 14 plus or minus the square root of 100, which is 10 over 2. So that's going to equal, let's see, I have 2. If I go 14 plus 2 is 12. And then if I go 14 minus 2, I get 2. So when I factor this out, negative 12, sorry. Wait a minute. I don't have that right. It's negative 14 plus 10. Yeah, that's right. Negative 12 and negative 2. Sorry. So s plus 12 times s plus 2. That what you got, Arthur?
Yes, it is.
Okay, thank you.
I'm trying to do PFE right now.
Yep. One more minute. One person is done. Good. 2, 3, 4. Okay. Nice. Because that's what I'm hoping for, is that you can do these now fairly quickly. So when you see one on the test, it's 3 minutes or less. So let's go through. Partial fraction expansion. If you can't do it in 3 minutes or less, don't get panicked. I'm not telling you that to get afraid. I'm just telling you, go when we first presented this material, how long would it have taken you to find these versus now? So you're becoming more proficient at it. Plus B over S plus 12 plus C over S plus 2. So A is going to be 168 over S squared plus 14S plus 24, evaluated at S equals 0. 168 over 24. Let's see. Does that work out to be 7? I think that's 7. B 168 over S times S plus 2, evaluated at S equals minus 12. 168 over minus 12 times minus 10. 168 over 120. We'll just leave it at that because we can't make that a whole number or an integer. And then lastly, 168 over S times S plus 2, evaluated S equals negative 2. 168 over, not negative 2, 12. There we go. So that becomes negative 2 times positive 10. 168 over 20. So now I can write this as 7 over S plus 168 over 120 times 1 over S plus 12 plus, or minus, I should say, 168 over 20 times 1 over S plus 2. So I2 of t is 7 plus 168 over 120 e to the minus 12t minus 168 over 20 e to the minus 2t. Now to solve for I1t, you have to do the same thing, okay? But if we can use matrices, we can end up with a lot more proficiency, a lot faster. So this is called a slightly more advanced topic. We probably won't get into too much, but this is called modern control systems analysis, where you do everything in a matrix and you can get the state of everything. Like I can directly solve for I1 and I2 if I have the ability to process it in matrices. I just wanted to show you that what we have over here, the 7 over 6, minus 8.4 over S plus 2 plus 1.4 over S plus 12 is what we got. We just had a lot of brute force analysis to do it. The top one we didn't even bother doing, but it would be the same process over again. So if we can do modern, it makes it easier. But more importantly, it's just mesh analysis. That's all it is. Nothing more than mesh analysis. Okay. So if you're going to do classical systems, you really want to know, or try to as quickly as possible, what is my end product? What am I trying to get? and see if you can just write a single equation to get that. It's much faster. So in this case, but I was asking for the mesh current, so there's nothing I could do. I needed both of them. But like, say I wanted the voltage across the 48 ohm resistor, what would I have done? I probably would have done a bunch of series parallel combinations, because that's the other thing too. If I go over here and look at my original circuit, let's say I wanted to get the voltage across the 42 ohm resistor. This is perfectly fine in Laplace world. And I'll actually show this as a box, not as a resistor. Because this equivalent resistor in the Laplace domain is 42 in parallel with 10s plus 48. It's just a resistor. So now I can do voltage divider if I wanted to. So you can see, like, sometimes it's just faster and easier to combine things. All right. Any questions on what I did? Because I just did voltage divider. I just did a series parallel combination, which their Laplace domain will call them resistors for lack of a better term. And we can get our results. Okay. So we'll check the results, and then we're going to see, we can see that I1 of infinity equals 15, and I2 of infinity is going to equal 7. Let's go back to the circuit. If both of these are replaced with short circuits, what do I end up seeing? I have 336. So the I1 of infinity is equal to 336 divided by the parallel combination of 42 and 48. What about I2? That's 336 divided by 48, right? So you can see that that equals 7. And the other one equals, I think it's 15 is what it works out to be. So we're feeling pretty good about our numbers because they make sense. What about 0? How about I1 of 0? What is I1 of 0 supposed to be equal to? 0. So let's plug in 0. 15 minus 14, e to the minus 0 is 1, minus e to the minus 12t, where t is equal to 0 is equals 0, doesn't it? Let's check the other one. I2 of 0, 7 minus 8.4, because that's 0, plus 1.4. What does that equal? 0. So the initial condition and the final conditions match with what we had. And the benefit is, remember how we had to do all the circuit analysis before? Draw the circuit at t equals 0, minus, draw the circuit at t equals 0 plus perhaps, and then draw the circuit at t equals infinity, and then do all these calculations. Over here, you just draw one circuit and you do whatever circuit analysis, and it gives you the time domain equation for any period in time. Oh, somebody has a question. Did anyone else get that? Yes, that's the answer in the book. So yes, I got that.
Yeah, I saw that after you went to the slide. Thank you, though.
Yeah, no problem. So the transfer function is going to have a lot of variables in it. Okay, and what is a transfer function? You've seen transfer functions already. All of you have taken circuit analysis with John. Electronics, maybe Homa hasn't. Did you take a class where you looked at something like this? Seen that? Anybody not seen that? You can say, no, I haven't seen it. It's perfectly fine. Especially if you haven't had, that's 342 for EETs here. What's that? Or is it 241?
Oh, no, it was 240.
241? You did 330? Did you have op amps down at SM?
Yeah, we were.
Okay. Electronics 1 or electronics 2, or do not have?
There was one of them, we had one.
Okay. So what is the gain of this system?
Negative RF over RI.
Be careful, I didn't give you enough information. I said the gain of the system.
Ah.
My closed loop gain, right? So we need to append that. What is the definition of the closed loop gain of the system? Isn't that V out over VN? Didn't you learn that? If I take V out and multiply it by the gain, isn't this in parentheses the equation or the variable that transfers the input to the output?
Yep.
Vn is, or V1, whatever you want to call it, is whatever value. It could be a sine wave, it could be DC. Multiplying it by negative RF over RI, now it becomes the output, right? So the open loop gain is also called the transfer function. Okay? So you can write a transfer function for anything. An input current to an output voltage, an input voltage to an output current. That's in electrical circuits. Can you think of anything else? In the process control industry, you can have a valve that the input can be a pneumatic symbol, a signal, actual air going into a diaphragm that pushes or pulls on or pushes down or up on a diaphragm, and that opens or closes the valve. Those are called air operated valves, and that would have a transfer function depending on the amount of air that goes in or out is how much that valve opens or closes. You don't see a lot of those valves anymore because it's almost always been replaced by electrically operated valves. They'll have an I to P or maybe an actual direct current to position valve. And if you give it like 7 milliamps, it opens the valve up to a certain amount. So it wasn't that long ago when I worked at the nuclear power plant. This is back in 92, which maybe that was a long time ago. The nuclear power plant was designed in the 60s. So yeah, that's a really long time ago. But that's how they actually did a lot of control valves. They actually used air to go ahead and open up to a certain level or close to a certain level. Now, I don't think you can find air operated valves anymore. Let me see. Humor and old guys. See if they still make them. These are not the ones. You can see over here, there's a little port for the air coming in. But the ones that I used to have had a giant diaphragm on the top. Let's see. I can't remember the name of the companies that made them. Like here. This is the one that they used to have. So they had this giant diaphragm on the top, and the valve, the little electrical control signal, would put air above or below to either push or pull on the valve. Now all control valves they're all done with here. No more air. Way more repeatable, way more reliable. Do you know what the company, this is at Maine Yankee, which is now, you know, Maine Dirt basically, because they tore it down. But do you know what they actually used? Or what was the biggest work that they had to do for all these valves? It's one really obvious answer. Anybody here ever been to an auto shop?
Yep.
When you walk in, what do you notice? Maybe. You hear a lot of
The big old
pressure
tank
leaking,
compressor.
right?
Yeah.
So can you imagine you have 5,000 valves with little 1/4 inch or even 3/8 inch lines that would run all over through the plant. So they'd have a common header and they'd have these tiny little valve lines that would go and control these valves. They were constantly fixing air leaks. Over here, no air leaks. And what's the other advantage? If your air is leaking, you get a pressure drop and you got to go find it, right? But over here, it'll tell you my wire is broken because I should be getting 4 milliamps, but I'm getting 0 milliamps, which is indicative of the fact that it's a broken line. That's why we don't start at 0 milliamps, we start at 4, right? If I should always get 4 milliamps and all of a sudden it goes to 0, hey, it's got a broken wire here. So you can go out very quickly and troubleshoot it.
So that just has to send a steady DC 4 to 20 milliamps to operate it. It doesn't have to pulse width or anything like that.
Nope, it's a constant 4 milliamps is at the 0 position. Now, this is maybe even changing a little bit more too, because what is replacing kind of electricity? It's all digital, right? So instead of having a valve with a wire going to it, you could wirelessly transmit to the valve. And as long as it has a power source, it still needs a power source. So it's not wireless truly, but it needs some sort of power to be able to open those valves. You don't see a ton of acceptance as of that yet, because we still don't trust computers, right? They can be hacked. So you're seeing a little more interest in it, but it's still kind of in its infancy. And so is it really worthwhile, to do everything wireless if you could save, some of the cabling? Maybe, but the 4 to 20 milliamps, that's really small cable. It's fancy cable, it's shielded cable, it's twisted shielded pair, so you have no noise, but it's pretty fancy stuff.
I think that's the bulk of the concern with, wireless is, if it's in an electrically noisy environment, the radio frequency could get degraded.
It is, but what's the nice thing about digital, right? There's always a packet with a bit or a bunch of bits at the end or the beginning telling you what you should expect. And if it comes back and then you think you missed a bit, it'll give you an error. So there's a lot of built-in error checking with computer stuff that you don't even realize is happening. So yes, with the wireless and if it's terribly noisy, you can't run wireless, but you can do things with spread spectrum. You have much better radios and receivers that can work through a lot of noise. Obviously, if you're getting a lot of spikes, a lot of powerful spikes, you can do that. But that's why we run twisted shielded pair, because as long as the emanating source is in a clean, noise-clean environment, that you can be spiking up and down all along. And as long as you set up the circuit correctly, you'll get no noise on your wires. Okay. So with our transfer function, we can have S terms in our numerator and S terms in the denominator. And the end result of that is we can actually define what we call poles and zeros. And we'll keep looking at that more and more. But a zero is the root or a root, so we'll put roots, of the numerator. Poles are the roots of the denominator. So why do we call it a zero? Because if you evaluate at one of the roots of the numerator, if you evaluate it at that root, it evaluates to 0, right? In the denominator, we don't call it a 0, we call it a pole, because if you evaluate at that root, the equation blows to infinity, correct? So one of the things, and we'll spend some time, well, I guess we'll do it here, is you can draw what's called a pole zero map of your system transfer function, not necessarily your input, but your system transfer function. And the reason why we want to do that is because we can tell a lot about the performance of a system just looking at the pole zero map. So again, we'll spend a lot more time looking at it at later points in the semester, but I should say next semester, but the idea of a pole zero map is I'm just plotting all the poles and zeros in the S-plane. And you can see I have the real and the imaginary axis. And now what I'm going to do is I'm just going to basically say, well, how fast is something? Or how much does it oscillate? How much does it overshoot? And you can look at these pole zero maps and be able to determine where or what the performance is based on its location. The x's are the roots of the denominator. See, these are the poles. What do you think would be the symbol we would use for zeros?
A 0.
A 0, yeah. Let's make it a 0. So it's really
This is-
obvious, right? The zeros are denoted with a 0, and the poles are denominated with x's. One last thing, you must have complex conjugate pairs, because remember when we do the quadratic equation, we have that plus or minus j term. So if you are off the real axis, right? If you're not living on the real axis, you know for a fact that you will have complex conjugates. So what I'm saying is, don't expect to see something like this and nothing directly across from it. If there's nothing directly across from it, you made a mistake. Okay? And we don't plot the poles of the input because the input can change. Sometimes it's DC, sometimes it's a sine wave, sometimes it's a decaying exponential. I don't care really what the input is, as long as the input is bounded, which means it doesn't blow to infinity, right? It doesn't just keep increasing its energy source. Then we hope to evaluate if the output is bounded. And we want to make sure the output is bounded. Okay? So let's see. So the poles and zeros, like we said, we talked about having a transfer function that has an actual system response. That's denoted as the transient response. That's how the system dies or does whatever it's supposed to do, or increases exponentially. My steady state term is based on what the input is. Okay, and knowing the poles, right? You can see the poles of H. That's going to give me my transient response. The input, which we'll call X, that's going to be the steady state response. Okay, that's what's forcing it, because we have to continue to supply energy. Then the coefficients that you determine from partial fraction expansion, the A, the B, the C, the D, on and on and on, all those are going to basically affect the relative magnitudes of your steady state and your transient response. They will not affect the characteristic in terms of, okay, does it look like a decaying exponential? Does it look like it has a steady state value or DC value? It won't affect that. It'll just affect the magnitudes that you would see. That's all it does. All right, let's do a linear ramp example. And then what do you think? Should I let you out a little early, maybe half an hour early so you can get to studying, or do you want to keep pounding new material? Pound new material?
Yeah, sure.
Sure to keep pounding material, Arthur?
Yes, let's do it. Hey, this is going to lead.
Minority.
This is going to lead to Bodie plots, isn't it?
I would love to do Bodie plots. I don't know if we have time to do Bodie plots this semester, because I want to make sure we get into Fourier series and Fourier transforms. Nobody's saying ick. Arthur, you've probably done Fourier series, right?
We had one question on the final with no homework. So yeah, let's not go there.
Okay. You have done Fourier series?
Done them a long time ago.
Okay.
I know that.
I would really like to get into Fourier series, because as the world becomes more and more chopped up with all these darn semiconductor devices, we'll go yell at John for that. The
Yeah.
world is getting more and more chaotic, and we have to analyze a lot of systems using harmonics. So that is something that is more and more important to us. And unfortunately, that's a lot of math, even more than Laplace. And it's math that can get complicated. But the idea is that if you can understand the basics of it, you can actually look at things and sort of understand, where does the concept of a harmonic come from? And especially for those of you who are doing your senior projects, like for you guys, you might want to look at a THD, total harmonic distortion. In the word harmonic distortion, where does harmonic come from? It comes from the Fourier series. So that's where it's a pretty useful skill. And it used to be that it wasn't that important. But again, because of all the, like your power supplies, right? I've got my laptop power supply here that, I don't know if you can see it in TV land, but It's just a laptop power supply. It's a little blob plastic, and inside it's a bunch of semiconductors. They used to only have power supplies with transformers. So if you used to pick up a power supply, it was, the size of your hand and it weighed a ton, because inside there was a transformer, and that would smooth out a lot of the operation. Now it's a Class D amplifier.
Mhm.
Everybody know Class D?
Yep.
Anybody here super into car stereos?
What?
Real high power applications, like crazy high power applications. You use Class D amplifiers, which can get super duper efficient. I'll show you a former student of ours. I won't say his name right. Oh, made mugshots.
No.
He was not arrested, I believe, so.
Oh,
Ethan,
no.
oh, I spelled stereo wrong. Where is he? He's in Winslow, Maine. No. He does not.
Huh.
Sorry, I just got a sidetrack because he
Yeah,
was really into this.
I was once upon a time.
If I can't see it. There was not high quality.
Hmm.
He had his own little outfit.
He had a company, yes. And he made one of those. So let's just see. Yeah, but I don't think that was the right one. But anyway, his name is Ethan Poissonnier. I'm not pronouncing his or saying his name right, but
But isn't your last name French also?
it is. But his is much harder to say than mine. So you see this woman? This is the type of stuff that he would build.
Yeah.
So you see when they turn it on, that's what his hair would do. And there's videos of him actually like his hair. And so he would actually replace all his glass with plexiglass because the glass would break.
Yeah.
It was like 30,000 amps,
Some of
30,000
them-
watts.
Some of it's enough that you can see it. The camera will capture it where the whole car body is distorting.
Yeah. I don't know if I can find him. I guess I can't find him, so. But it was terrible quality. It was just something that was super, super loud. And he would turn it up. And like I said, like 125,000 watts in a car. I mean, it's absolutely insane. But yeah, I don't know. I don't see it. So sorry. If it was in Winslow, let me try one last one and then I will punt on this. No, I don't see it.
Should I just taken the last name out?
I can try it. Let's see. But he graduated on 5 years ago, and that's what he did. He did a senior project one that did it, and his was just like that crazy loud, absurd, whatever. So anyway,
And now I have tinnitus from it. Yay.
exactly. Yeah, I get tinnitus, which means you get like a high frequency sound permanently. But so yeah, so we'll look at harmonics because that's where you don't care about it, but most of the time you do, right? You want really low total harmonic distortion. So the artist actually wants you to hear what they hear, and so they want higher quality. So let's do a linear ramp one, which means no longer unit step, but a 50 times T. That's the ramp, right? Because the T increases. Let's take it to the Laplace domain. Now what we're doing is we're looking for the V out. So I'm just going to use voltage divider. Works perfectly fine to use voltage divider, right? So actually, I'm not going to do voltage divider. I'll do nodal analysis. So nodal analysis, V out minus VG divided by 1,000. So this is VG up here, and obviously this is V out. So the current here here and here is what I'm doing the nodal analysis for. So V out minus VG divided by 1,000 plus V out over 250 plus 0.05 S plus V out over 10 to the 6 S. Now I just did some fancy math and I did it all in one fell swoop. So that's the hardest part about a lot of this work is just making the math so that you get pretty easy equations. And then my transfer function, which is V out given an input, VG is equal to 1,000 times S plus 500 over S squared plus 6,000 S plus 2.5 times 10 to the 7. Very first thing I'm going to do is do the quadratic equation to solve for the roots. And I end up with negative 3,000 plus J 4,000. So I notice that I have an input of 50S squared, and it's repeated, right? So I'm going to have to do my partial fraction expansion. And notice, I don't do partial fraction expansion here, because this is just going to look like this, right? That would not need partial fraction expansion, but that's just a system. It doesn't actually tell me what the output is until I energize the system. So I have to do partial fraction expansion here. There's repeating roots, so I have 3 cases. Sorry, I have the standard case, the repeating roots case, and I have a complex number. So let's go ahead and solve for let's solve for B. So I multiply both sides by the highest order root, S squared, and then I evaluate at S equals 0. And then, where did I calculate B? I guess I didn't calculate B here. Sorry about that. So B is going to be equal to 5 times 10 to the 4th times 0 plus 5 times 10 to the 3rd all over 2.5 times 10 to the 7th, right? When I evaluated S equals 0. So I have 25 times 10 to the 7th over 2.5 times 10 to the 7th. The 10 to the 7ths cancel, so B is going to equal to 10. Is that fancy math too, or is that just taking advantage of using the powers of 10 and making it really easy? Right, when I multiply 2 to the 4th by 2 to the 3rd, that becomes 10 to the 4th times 10 to the 3rd, that becomes 10 to the 7th, right? And then I can just divide it out. So I've got B equal 10. Now to solve for C, I'm going to still multiply by the highest order S term, but now I'm going to take the derivative and then evaluate at the root. And what I end up with is C equals minus 10,000. And then B, did I solve for B yet? I did not. So how would you solve for B? Or I'm sorry, A at an angle of theta. A at an angle of theta is equal to 5 times 10 to the 4th times S plus 5 times 10 to the 3rd all over S squared, evaluate at the positive real root. Now, I'd have to stick that in my calculator. I can't do that in the top of my head. But I've done that for you already. And I've got square root of 5 milli times the 4K at an angle of 169.7. So bringing this back to the time domain, here's my V out of T. I didn't actually calculate B at an angle of theta or A at an angle of theta or B. I showed you how to do B, and then A at an angle of theta, you just have to plug that in. All right. And here's what that plot looks like. You can see you have a linear escalation, so that's the value of 50 times T. And then the blue line is the actual output. And so you can see there's a gap, right? Because you have this decaying exponential here that is making your life a little harder. So that's why you see the gap. And then eventually over time, they balance each other out. They would be at the same value. Okay? All right, I'll let you go. 25 minutes ahead. How magnanimous am I? Any questions?
Cover again. Repeating.
Right here. Did it right here. We just solved for B. So
I know.
okay. Hold on. Let me write it down. Go ahead.
So, 5.
So we want to take that to the time domain, which means we need to do partial fraction expansion. So we just do all our terms, a over s squared plus b over s, because we got to take it all the way down, plus c over s plus 1. Okay? A is easy. You multiply both sides by whatever is under the a coefficient. So 5 over s plus 1, evaluated at s equals 0 is equal to a. That's equal to 5. To do b, I'm going to do the same thing. Multiply both sides by whatever is under the a term, the highest order coefficient. And I'm just showing it out like I just multiplied both sides. Now, I'm going to take the derivative with respect to s because, oh, it's not moving out. Take the derivative of 5 over s plus 1 with respect to s. That goes to 0, right? That goes to b. And this is going to be, it's going to be some, well, let's go ahead and write it all the way out. So we've got c as a constant here. So it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared, right? You'll notice that there's always an s term, at least one s term that multiplies the c coefficient, right? So when I evaluate that at s equals 0, that term goes to 0. So all I'm left with is b. So if I take the derivative of 5 times s plus 1 with respect to s, I'm going to end up with the derivative of the numerator, which is 0, times s plus 1, minus the derivative of the denominator times the numerator over the denominator squared. And I evaluate that at s equal 0, and that's going to be equal to b, right? So b is going to be equal to -5 over 0 plus 1 squared, which is -5. That's how I do the repeating roots. C is regular old standard way. So go back all the way over here. C is equal to 5 over s squared, evaluated at s equal -1.
Okay, so you only do the derivative.
The repeating root. Because otherwise than that, it all cancels out, right? When I do the regular evaluation. So that term drops out. That's it. That answer your question, Austin? Was that an easier one?
Yeah,
You didn't like,
in 25 minutes, I want to be good on the test. I can do it. I don't feel like that.
I'm happy to keep doing more.
Yeah.
It's up to you. Give me another one.
Go ahead. Okay. Yeah.
Well, we can just create one, right? We can say f of s, and let's make this one a little more challenging. Let's go s plus 1 over s plus 2 squared times, we'll make this one just s. That okay? So that's equal to a over s plus 2 squared plus b over s plus 2 plus C over S, right? A is the easy one. That's S plus 1 over S evaluated at S equals -2. So that's -2 plus 1 over -2, which is equal to 1/2. B, now I got to do the derivative, right? So I've got to take the derivative of S plus 1 over S and evaluate that, take the derivative of that and evaluate that at S equals -2. So the derivative of that is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared, right? That's going to be equal to my B term when I evaluate that at S equals -2. So I have -2 minus 1 times -2 plus 1 all over -2 quantity squared. So that's equal to -2 minus 1 times -1 is +1. So that's -1 over 2 squared, 4. So -1/4. And then my C term, C is S plus 1 over S plus 2 squared, evaluated at S equals 0, 1/4. So this becomes 1/2 times 1 plus 2 quantity squared plus or minus, we'll just put -1/4, 1 over S plus 2 plus 1/4 times 1 over S. This one we have to be careful, right? Because that's T, e to the -2t. And remember, this has to be n factorial, right? So n factorial here is, well, this 2 is equal to n plus 1, right? So n is equal to 1. So what we have is in the time domain, t, e to the -2t, still got my 1/2 up front, minus 1/4, e to the -2t, plus 1. And that is my f of t. So it's the same process over and over and over again. That's what we're trying to do, right? As engineers, if we can have a process that's repeatable and works for all cases, it sort of becomes second nature. You just keep doing it over and over and over and over again. So we're doing sort of the same approach, but the modification we make here is to find for those lower order coefficients, you take the derivative. Now, here's the thing. If you hate doing derivatives, absolutely despise it, you can solve for A, just like before. Let's do that as step 1. Solve for C, just like you did before, right? And then to solve for B, you could do the old-fashioned way, right? Which is put these all back under one common fraction. And then you could solve for B if you don't like to do derivatives. But I don't suggest you do that. I just say you do the derivative. Okay?
You have to insert it.
The f of t?
Yeah. So that last, which was the C term, was 1 over.
No, it's 1/4. You're right. So that should be 1/4, I think. Yes, 1/4, not 1. Because I've got the 1/4 multiplier right here, right? So I got to include that there. So the way that I would do these is I would just, do partial fraction expansion. I would just practice. Practice, practice, practice. Just do it so that you can almost do these in your sleep. There's all kinds of, like if you go over here to edge, you should be able to find a bunch of images here. So like here's one over here. Here's one here. I mean, you can just do, and they have examples, so you can do all kinds of examples. This one actually shows kind of the same way that we're doing it. So yeah, you can find boatloads of examples by looking on the web. Any other questions? Feeling better? Worse? Same? I'm feeling much better. I'm very optimistic that tomorrow will go swimmingly.
Well, I'm glad you're optimistic.
You're not feeling so good about it? Because I know the first test, some of you all were not particularly satisfied with your grades, but again, that's just getting used to me and my tests. I try to get you to think. This one will be not quite as much thinking because it's not a lot of review, it's a lot of new material. So it'll be a little more plug and chuggy than it would be. And then when we get to my other classes, then you start to think more a little bit on tests. So that's all.
Yeah, kind of questions there will be.
7?
All right.
You get 2 hours and 50 minutes, right? Where's the test going to be? Right here. For those of us going to come live, 9 a.m. tomorrow morning. I will be here. TV land, just make sure your cameras are on.
Sure.
Unless you want to come and see our smiling faces. Arthur, we miss seeing you in person. You want to drive up?
No,
Like save on gas money.
well, not only that, but the time that I save driving up, I work, so.
Yeah. Well, it's an hour drive for you, right?
It's about 2 hours to get there and 2 hours back.
Oh my goodness. I thought you were an MDI. I thought that was about 50 miles, but I guess
No,
it didn't include traffic.
it's almost 70 on the nose.
Oh, okay.
And yes, there's, perpetual construction, so that makes it worse.
Well, 1A has become the worst road in Maine to drive on, so at
Yeah,
least
and I
from
wish they
Bangor
would-
or Brewer to
to Ellsworth. it's about-
MDI is a mess.
Yeah.
Yeah, not even MDI, because that's why you gotta take Route 3, but yeah, it's a disaster. It's 20 miles of how not to do road construction, I guess, so.
Bypass. We need a bypass.
I'm gonna just cut down some prime property there, so. All right, that's all I had. Had a great day. I look forward to seeing you all tomorrow. Take care, everyone.
All right. Thank you so much, Paul.
Thank you.
Thank you very much, Paul.
Thank you.
Three,
Thank you, Paul.
Thanks, Brandon.